So guys, I hope you are loving this course. Now we enter into the phase 4 of this course, which involves splitting and merging of data blocks. So first we will going to learn how to split data blocks. So when our Linux Memory Manager requests a fresh virtual memory page from the kernel for memory allocation to the application, then that complete virtual memory page is actually available to satisfy the memory request of the application. It means that this entire virtual memory page will act as one free big data block. So we already know that every data block is guarded by its meta block. Therefore, as soon as our Linux Memory Manager requests a fresh data virtual memory page from the kernel, our Linux Memory Manager will going to treat this new virtual memory page as a free data block, right? So what we need to do is to create a meta block, mark it as true, and this meta block is a guardian of the data block whose size is 4068 bytes. This meta block is also the lowest meta block present in this virtual memory page, and this meta block is also the topmost meta block present in this virtual memory page. Therefore, previous and next pointers will going to be null, right? Now let us assume that the size of the virtual memory page on the system is 4096 bytes. It is for this reason that you subtract the size of the meta block and it gives the size of 4068 bytes, right? So 4068 bytes of the memory is available in order to satisfy the new malloc request coming from the application. So as soon as our Linux Memory Manager requests a new data virtual memory page from the kernel, we will going to treat that particular virtual memory page as one big free data block. Now let us discuss how things pick up from here. Suppose the application issues the request to allocate a memory for the object of type foo, right? So let us assume that the size of this data structure is 20 bytes. Now our Linux Memory Manager will going to make use of this virtual memory page, and our Linux Memory Manager will going to make use of this available white region in order to satisfy the memory request of the application. So I'm now drawing a second diagram of the same virtual memory page. But now this will be the snapshot of the virtual memory page after our Linux Memory Manager has satisfied the request of 20 bytes of the application. So you can see that the same meta block is now updated as per the 20 byte data block whose guardian it is now. So isFree boolean is set to false, the block size is set to 20 bytes, the previous block is still null, and the next block will going to be the pointer to the next meta block number 2. We need to create a new meta block MB2 so that we can store the meta information of the remaining free block of this virtual memory page. So you can see that isFree is set to true. It means that the data block which this meta block is protecting is free and is available for memory allocation. The size of this data block is 4020 bytes. The previous block is updated to point to the starting address of the meta block 1, and the next pointer of this meta block is set to null. So if you analyze this process, in order to satisfy the malloc request of the application, the free data block of size 4068 bytes is splitted up into data block which is used for memory allocation to the application, and the remaining portion is still available for memory allocation to the application, right? We need to create one more meta block MB2 in order to store meta information of the free data block of size 4020 bytes. So now let us take another example. Suppose the application issues another request of size 20 bytes, right? Now the same virtual memory page would look something like this. You can see that there is absolutely no change in meta block 1. But now the meta block 2 will be used in order to satisfy the malloc request of the application. So you can see that isFree is set from true to false, the block size is set to 20 bytes, the previous block is updated to MB1 and the next block is updated to MB3. We will going to create a new meta block MB3 because we need to store the meta information of the rest of the virtual memory page which is still available for memory allocation, right? So you can see that as more and more malloc request of the application comes, the size of the free data block shrinks, and it is quite obvious. Note that throughout this example, we have assumed that the size of the meta block is 28 bytes, which is fixed. And also note that I am not showing the offset field of these meta blocks in this example because it is not required. So the points to take away from this slide is that for every malloc, a free block is splitted up into allocated block and the remaining area left is a smaller free block, right? So in this example, the data block of size 4068 bytes was splitted up into data block this one as well as the free block this one, right? If virtual memory page do not have a free block to satisfy a malloc request, a new data virtual memory page is requested from the kernel and same exercise is repeated, right? This is quite obvious. So next we will going to dive a little more deeper and understand the mechanism of block splitting at a more finer level. For now we have understood that a free data block is splitted up into a data block which is allocated to the application and the remaining free data block which is still available for memory allocation. So this process is called block splitting. So always remember that it is the malloc request which results in block splitting. Free calls never results in block splitting. We will see that free calls actually leads to block merging and not splitting.